Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY 212, we are at the lecture number 18 and the topic is the correspondence principle and Dirac notation. The idea of correspondence principle is that quantum mechanics reduces to classical mechanics in the limit of large values of quantum numbers and also the small value of Planck constant or reduced Planck constant. And in today's lecture we will talk about the correspondence principle, and also the next topic would be the Dirac notation. Dirac invented the notation for wave function and its complex conjugate that makes many calculations simple and intuitive. So we will also talk about the properties of Dirac notation. So let's first start with the idea of correspondence principle, but in order to build the idea, we will first review the example of one-dimensional box. One-dimensional box means that a particle, for example an electron, is confined into a one-dimensional box, and there are many properties related to quantum mechanics which are revealed when we discuss and describe the one-dimensional box. This one-dimensional box can be realized practically by having impenetrable walls, and let's consider that there is a string which is stretched between these two walls, and this string is infinitely thin and it is also frictionless. So we can have a particle, as I said, like electron, which is moving on the string, but it is confined to move, it is constrained to move only on the string, and it cannot go in other directions, for example upwards or downwards. That's why it is constituting a one-dimensional box. And since it can also not leave the walls, it cannot go to the walls, it is constrained from one side and from other side as well. That's why it is an example, practical example of a one-dimensional box. And we also consider that this is a point mass. For example, electron can be ideally considered as a point mass particle, and also the length of this string is considered to be of size A. So this whole assembly is constituting the one-dimensional box. Now we will see that how can we realize the correspondence principle from this example. So let us consider that the initial position of this point particle is not known to us. So it is moving, but we don't know where it started. So in order to make it concrete, this is the equation for the motion or for the position of this one-dimensional system of this point particle, maybe electron, and this x is its position at any time, and this x naught is actually its position at initial time. So we call it initial position of the particle, and v represents the velocity of the particle and t is the time. So this is very simple equation of the position for any particle. So x is the position at any time, x naught is the initial position, v is the velocity with which the particle is moving, and t is time. Okay, so now we also assume that x naught is completely unknown to us. So this is important consideration, that we don't know where it started or what is the initial position of the particle. This will then create some kind of uncertainty, and then if there is an uncertainty in the system, in order to know its final position, we will have to calculate the probability, and from there actually we will make the connection to the quantum mechanics. So the probability of finding the particle in some interval, let's say call this interval between x and x plus dx. So classically we want to know that what is the probability of finding the particle in this interval, that is between x and x plus dx. So keep in mind that we don't know the initial position. Now if we know the initial position, then it will be easier and the problem will be different to locate the particle in this interval. But since we don't know its initial position, then we have to just calculate the probability of finding the particle in this interval. So let me make a schematic diagram of it in this one-dimensional box. So let us consider this is the limits of the interval. It starts at x and it goes to x plus dx. So what we want to know that in this interval, actually in this interval, we want to know the probability of finding the particle at any point inside this interval. So classically, if we want to calculate the probability of particle to be here, then we first have to know that what is the time that the particle spends in this interval, and then we will divide this time over the total time the particle is taking in order to move on the string, and then from this we will be able to calculate the probability. So let's do some mathematics in order to calculate this probability. So in this equation you can see on the left side, this is the probability p, this first term over here, this is the probability p of finding the particle in this interval dx. So this will be equal to the time delta t. So this is the delta t time which the particle actually takes to move between, or it is the time it spends in this interval, and divided by the total time it is present on the complete string. So this ratio will give us the probability of finding the particle in this interval. So imagine that somebody is in some building and for 1 hour, and then that person spends let's say 10 minutes in one of the rooms. So the total probability of finding that person in that room will be 10 minutes by 60 minutes because in that interval this is that was the time that person was present in some particular room. So in similar intuition we developed that the probability is the time the particle is having in the interval x and x plus dx divided by the total time. But then we can replace 1 over t by v by a, because the length of the string is a and v is the velocity with which it is moving. So from the simple equation s is equal to vt, from here you can see that since s is equal to a and v and t is the total time, so you know that 1 over t will be equal to 1 over a, you can put over here. And then since v dt is equal to dx, that is the length of the interval, so we have that dx, so total probability in this interval is then dx by a. Since dx is the interval, so it means that the probability is proportional to 1 over a, but 1 over a is constant, so it means that probability is constant. So that actually means that the probability of finding the particle on the string of length a is constant. That means it's same everywhere, that it is equally probable to find the particle at any position. If you want to draw this, you will get the classical probability like this. So this is the length of the string at the x-axis, which is equal to a, and this is the probability, which is equal to 1 over a. So you can see that since it is constant, so it does not change. So probability of finding the particle at any position on the string is same. So we have equal probability of finding the particle everywhere on the string. So this is the classical probability we calculated. And as I said initially, that in the beginning of the lecture, that the correspondence principle will be realized through matching the classical probability and quantum mechanical probability, and we have taken then the example of one-dimensional box. So let's go to the quantum mechanical probability and let's see if we can compare these two probabilities in some limit and then we'll be able to define the correspondence principle. Quantum mechanically, the probability, as we discussed in the last lecture, if you remember, the probability of finding the particle is dependent on the wave function phi, which the eigen functions, and also the energies En. So we plotted the En and phi n. So in this case, imagine that n is equal to 3. So in case of n is equal to 3, then we will have phi 3, and in phi 3 case, we will also have the probability Pn, that is, in this case we will have P3. So here you can see that in case of P1 you have this probability, which means that the particle is having high probability. This is a Gaussian probability at the center, but when you go to the P2, then you have 2 peaks, but when you go to the P3, then you have 3 peaks. That means that what is the probability of quantum mechanically, it is most probable to find the particle on this position and on this position and on this position, and the probability of finding the particle on these position is 0. So here, here and here the probability is actually maximum, and in these points here, here, here and here the probability is actually minimum, and in between then you can know that what are the values of the probabilities. But this was the case only for P3. Imagine that we go to the limit when n is actually very large, so you can say maybe infinity. So when this is the case, then you can see that this probability intervals will be very small, because compare in this diagram the P2 and P3. In P2 you see 2 peaks, but in P3 you see 3 peaks. And similarly, if you go higher, P4 will have 4 peaks and 5 peaks and so on. So in case when n is very large, we will have infinite many peaks. So for considerably large n, the diagram would be something like this. So you can see many peaks over here. So probably this is the case of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So it is roughly speaking P 20, and in case of P20 you can see the 20 peaks over here. But if you have when n is very large, that is going to infinity, you can imagine that you will have a straight line over here, and all the points are so close actually that you will not be able to know this difference between them. So peaks will not be visible, and you will see that all the points on the line are equally probable. So when that is the case, it means that we are getting the classical probability from the quantum probability, but only when n is very large, that is n is infinite. So this was the correspondence principle, and it was given by Bohr. That's why it's sometimes called also the Bohr correspondence principle, which says that when quantum number, because this n is quantum number, so when n is very large, our principal quantum number is very large, that is n is going to infinity, the classical mechanics is achieved, or the quantum mechanics reduces to classical mechanics. This principle has been seen and verified in many examples. I will give just one example, and therefore it is confirmed that classical mechanics is the limiting case of quantum mechanics, and the limit is that when n tends to infinity. So Bohr correspondence principle says that in the limit when n tends to infinity, and also h bar becomes small. So what is the reason for this thing, that is h bar is equal to small? So since h bar is a quantum mechanical parameter, and we know that in all classical phenomena or all classical formulas, we haven't seen the h or h bar. H bar is actually h by 2 pi. It is called the reduced Planck constant. So it means that if h bar is 0, we shall also have the same classical limit. And it has been also observed that whenever the calculations are made and h bar is taken as a very small parameter, and its leading term when we Taylor expand, the leading term where h bar is 0 actually gives the classical results, and when h bar is having some contributions, then these are called the quantum corrections. This is one way of quantization as well, by the way, when we perturbatively calculate the quantum mechanical results, and in the leading term h bar is 0, and then h bar square and h bar higher order terms are giving the corrections which we call quantum mechanical correction. So the Bohr correspondence principle then tells us that in the limit when n tends to infinity or h bar becomes small, we have our quantum mechanics reduced to classical mechanics. So one of the examples of the Bohr correspondence principle is the case when Rutherford calculated the classical done the classical calculation of Coulomb cross section in case of many particles scattering. So when he did these calculations in classical case, and then when quantum mechanical calculations are done where these two limits, that is h bar tends to 0 or n tends to infinity, were applied, then the both results matched. So so it was somehow proven that the correspondence principle is true, and it was then again seen in many other examples as well. So far so good for the correspondence principle. Now we move toward our next subtopic, that is called Dirac notation. So Dirac notation is, in principle, is a notation. It's just a way of writing things, but it is so convenient and easy that this notation is used quite often in quantum mechanics. So what this notation is actually, so in this integral you see on the right side the wave function psi, or not actually wave function, it's complex conjugate, and you see the wave function phi, and you see the product of them under this integral. So Dirac invented another way of writing this product under the integral, and that is on the left side. So on the left side you see psi and phi, and these are in the angle brackets, and from the bracket then Dirac given the name to this notation as to the left side bracket is bra, and the right side of the bracket is cat. So this complex conjugate of psi star was then represented with a psi, and the original function, the real function, is represented with the cat, and this integral is represented by this line between them, and this whole thing is actually equal to this integral on the right side. So this is actually the take. So there are two steps actually to calculate the integral of this product. First is to take the complex conjugate of one of the wave functions you want to calculate the product of it, and the second step is to integrate this product, and this will give you the probability. But the Dirac notation for this complex way of writing is very simple, that we write this in terms of angle brackets, and the complex conjugate is bra, and or the first part of the bracket, word bracket, and the this phi is, or the real part is the second part of the bracket, that is cat. So this is the Dirac notation, but it is not very I mean, it's not very trivial. This notation has many good properties, and let's talk about these properties one by one. First one is that this psi star must be finite, that is, it cannot be infinite. So when we assume that it is finite, then if we have some complex number a, and it is or you can say a real number, because here you can see that this in this cat this a is multiplied with a phi, so it is equivalent to, when you take this a outside over here, so it came over here outside. So these in the Dirac notation we have this property, and that you can just pull this a out of the integral, because integral is not dependent upon it. So in this case you can just take it out from this angle bracket product, and write it outside. And the second property is that if this A is with a bra, then it will be complex conjugate of it, because A is a complex number. But you can still pull this out of this integral, because it is again a constant, and integral does not depend upon it, so we can pull it out. So these were the two simple properties with respect to some complex number. And then we have that if psi phi star, you take star, a conjugate of it, of this integral in bracket notation, and if you change the order, that is phi comes here and psi comes here, or you can say that you take the complex conjugate and it comes equal to this. So taking complex conjugate just reverses the order of it, because phi star would be then phi and psi star would be then psi, so it just reverses or changes the order. The next is the linear property, where you can see that there are two wave functions phi and psi, and they are under this operator are linear. That is, we can write this, we can take phi and psi, or we can take psi first and phi second, and then add them. So you add them and take the ket of them, or you separately take the ket of them and then add them. So this property is called linear property. So it has this Dirac notation is actually linear. The next thing is about the product of linear sum of two wave functions. So psi 1 plus psi 2 star and phi 1 phi 2. So this will be equal to psi 1 psi 2 and phi 1 phi 2 in terms of the bracket notation, as you see over here. So how to multiply this to get this thing here in the bracket notation? You can guess that what we will do, that we will multiply first ket with the ket and bra with the bra, and then ket with the bra and bra with the ket. So we will get 4 terms, as you can see here. This one, psi 1 with a phi 1, psi 1 with a phi 2, and then psi 2 with a phi 1 and psi 2 with a phi 2. And in this way, you see that we form the product in the bracket notation. So it's in some sense simpler than the calculation in the under the integral. So in today's lecture, we have seen the two topics, that is the Bohr correspondence principle, which is very important to note conceptually, that quantum mechanics actually reduces to classical mechanics, but in the limit of n very large, that is principal quantum number n is very large, then the results from classical mechanics and quantum mechanics match. And the other parameter is h bar. When h bar is 0, then the results from classical and quantum mechanics again matches. This principle, when quantum mechanics reduces to classical mechanics, is called Bohr correspondence principle. And the next thing was the famous Dirac notation, and we have seen that under the integral we can use the bracket notation for the wave functions and its products and addition and other properties. So with this, I hope you got the message of what the correspondence principle and Dirac notation is. Thank you very much.